All right, our third step in our problem solving strategy is to carry out the plan. So once you decide which plan you want to try, you're going to implement the strategy and perform any needed actions or computations. You're going to attend to precision in language and mathematics used. You're going to use the right words for the right things. Check each step along the way, either formally means like calculation, like you're going to do it twice, or informally, which means, does what I just did make sense? You know, you're just sort of checking like, is your reasoning right? And then keep an accurate record of all work. I cannot tell you how frustrating it is when a student comes to my office or when my children comes into the kitchen at night and wants me to give them help and the work is all over the page and I don't know what they did. So I have a really difficult time of knowing where to start to help them. Do they have any clue what's going on, or are they just missing a negative along the way? You know what I mean? So if you will keep an accurate record of your work, a neat record of your work, it's a lot easier to get help when you do get stuck. And then the last step, number 4, is to check your work. And to check your work, there's 2 things you need to do. You need to decide if the answer is reasonable. Does it make sense? So when I was teaching as an undergrad, I was a graduate student and I was teaching undergrads at the University of Kansas, undoubtedly there was a question on a specific college algebra test every semester where the question asked how many termites did something or other. And we would all just roll our eyes every time students gave us an answer that said something like 42.37 termites. Right? It's not reasonable. It doesn't make any sense. You can't have a 0.37 of a termite. So either they did something wrong or at the very least they should have rounded at the end, right? So make sure that the answer makes sense. And then also to check the accuracy of the results. So accuracy has to do with whether or not the computations actually were correct. When I added 9 and 5, did I get 14 correct? Or did I accidentally write down 16, right? Those are accuracy issues. Both answers, 14 or 16, might be reasonable in the context of the question, but which one was accurate? All right, so what we're going to do next is we're going to try some of these problem-solving strategies. Some of these are very specific, and it's kind of like, this is a great example where you would use this. And some of them, like, there's other ways you could have done it too. And I'm just going to show you an example where you could use one of the strategies you may not have thought to use in that fashion. All right, here's our first one. There's a mathematician, famous mathematician named Gauss. That's how you pronounce his name, Gauss. This is Gauss's problem, and this is like really happened. He was in an early grade school, and his teacher gave the class an assignment intending it to take them a good deal of time. And I know as teachers you would never do such a thing to your students. That would just be terrible, right? She wanted to occupy them for a little while. So she asked them to find the sum of the numbers from 1 to 100. Okay, so she wanted to add 1 plus 2 plus 3 plus 4, all the way up to 100. And would you think that would take quite a bit of time? Sounds like a pretty good lengthy problem, right? Unfortunately, Gauss answered, well, fortunately, but you know, for the teacher, unfortunately, he answered almost immediately. So I'm going to show you his strategy and what he did. And his strategy had to do with the fact that he saw a pattern. Okay, so we're going to look at the pattern of what he did. So if you will write down with me, our work that we're writing down is to help us see the pattern, not necessarily that this is the work that he showed along the way, but this is the pattern he saw. Does that make sense? Okay, so I'd like for you to write down the numbers from 1 to 100, but we're just going to write the first 3 and the last 3 with a plus ... between them. Okay, so we're going to write down 1 plus 2. Actually, before I do that, let me start on the right, and we're going to write S equals S for sum, just so that we have a little notation to make it easier on us later. 1 plus 2 plus 3 plus, and then we're going to do that ... that I mentioned. And then we're going to write the last 3 numbers. So what would the last 3 numbers be? Right, 98, 99, and 100. And then what we're going to do is we're going to write them again, but in reverse order. Okay, so I'm going to start with the 100, and then the 98, and then the 97, and then the 321. Oh, what happened? Oh, you're right. Thank you so much. Let me fix that. 99 and 98 need to both be there, you bet. And then 3, 2, and 1. really small writing. Let's make it a little larger. Okay, so here's what the pattern is. The pattern is that if you take these numbers and pair them up and add them, what do you notice? They're all 101. They're all the same, right? That's a pretty cool feature. They're all the same. So if I add these all up, sort of like a big old giant addition problem, right? Draw a line, put a plus kind of thing. This is still S on the left. It's the same sum I had before. So what happens when I add S and S? I get 2S, and you know that from, advanced sort of mathematics, high school kind of mathematics, but at the very least, looking at that, you would say I doubled it because I added it to itself, right? That's where the 2 came from, really. These are all 101. Okay, now, I'm adding 101 together many, many times. How many times? How many of them are there? There's 100 of them, right? Because the original numbers were from 1 to 100. There's 100 of these guys. So this is 101 added together 100 times. So far, so good? There's 100 of them. There's got to be a faster way, even so, to add 101 together 100 times. Multiplication, right. So what could I do instead of adding 101 together 100 times? 100 times 101. Exactly. And again, this is double my sum. We're writing 2S. He probably did not write 2S as a young child, but he knew he doubled the sum. What is 100 times 101? 10,100. And then what would I need to do to find our actual sum? Divide it by 2. And where did the 2 come from again? Right. They are the 2 S's I added, but what is it in terms of the context of the problem? Why is there a 2? Right. But why is there, try to think of another way to ask.
Because you have 2 problems, like you have the 1, 2, 3, and then you flip it. So you're adding
Right.
together.
So this sum right here is my sum, and this is my sum twice, right? The reason there's a 2 is because my sum that I'm looking for is there twice. I've got twice as much as I really wanted to add together, right? That's where the 2 is coming from. It's because I've doubled the number of numbers I was supposed to add. So that's where it is coming from. All right, so what is 10,100 divided by 2? 5,050. So obviously Gauss was quite bright. He was not your average, whatever grade he was. Early childhood is all I think that it says in this particular problem, but he noticed patterns. That's what he did in the problem. So thinking about that idea of noticing patterns, we're going to do a similar problem next. We're going to find the sum from 36 to 147. And the way we're going to do that is by examining a similar case. And the similar case we're going to examine is the problem we just did, right? This is a similar type of question. It's quite similar. I'm adding a bunch of numbers together. We're going to talk about how to add these numbers together and how to add some other numbers together next time. So let me do this problem with you, and then we'll stop after this one. We'll start back at this problem next time and talk a little bit more about it with an additional sort of variation to this so you can see what else could be done. All right, so the problem starts out by writing exactly out what I already have. I'm not going to write them again because they're already on my paper and on yours. I'm just going to write S equals. What was the next thing that we did? We wrote them down flipped around. Okay, so we're going to flip all the numbers around. 147, 146, it would be 145, all the way down to 37 and 36. And again, pairing them up, we get what value? 183 for all of them, right? Whole bunch of 183s. How many 183s? It's not 147 of them, right? So how did you get 111? You're really close. Go ahead.
Subtracted 147 minus 36.
Okay, 147 minus 36, and I contend we actually need to subtract 35, but you're close. So here's how to think about it. If I'd started with the number 1 and I went all the way to 147, how many numbers would I have? 147. But I didn't start at 1. The first 35 numbers are sort of missing, right? So I subtracted off 35 because the first 35 were missing. So 147 minus 35, which is 112, are actually how many numbers I have. And this is double 2s, what I started with, right? It's double, so there's that 2 again. And what is an easier way of adding 183 together 112 times? Multiplying. So we'll do 183 times 112. And I'm not going to do that one in my head. Grab a calculator if you have it. What do you get? I only have the final number down, so I don't have this number down. Does anybody have a calculator? 183 times 112. What do we have?
40,496.
Okay, and then what would we do to find out our sum? Divide by 2 to remove the double counting, right? The double summationing. And the final result would be 10,248. So the other example, I'll mention it now so you guys can remind me that I want to start here next time. The other example that I want to sort of throw in here and talk about is what happens if they don't have all the numbers? What happens if they skip numbers? What happens if instead of it saying 36, 38, 37, 38, it was only evens? Or every 5th number or every 8th number, what would I do then? Okay, so it will change things just slightly. It's a variation on this same problem that I want to point out when we come back together next time.